Hey guys, today we're going to start chapter 2 with section 2.1, rates of change and the tangent line problem. You'll need a highlighter today, several different colored pens. You might want to have your calculator handy just in case we need that. Lots of highlighting today. We're going to start with defining average and the instantaneous rates of change at a point. In plane geometry, we've learned that a secant line is a line that intersects a circle or some other curve in two places. We also learned that a tangent line is a line that intersects a circle at one point. In our study of differential calculus, we need to clarify, classify, and truly understand these two big ideas. For general curves, we need a better definition. We will be concerned with a tangent line drawn at a point on a curve. Most of us believe that a tangent to a curve is a line that intersects the curve at exactly one point. However, in the figure below, you can see that the tangent line touches the curve at several points. So a better way to describe a tangent would be to say a tangent to a curve at a point is the line that best models or approximates the behavior of the curve at that point. So with the diagram that you see here, it is tangent to the curve at point P. It is not tangent to the curve at point Q. This idea will help us find the slope of the curve at a point. Also, that the slope of the curve at a specified point will be referred to as the slope of the tangent line, instantaneous rate of change, or derivative. So that slope is going to be present in each of those parts. The most important thing to note here is that the tangent to a curve at any given point is unique. A function f that has a defined slope at x equals a has two things in common with its tangent at x equals a. The point of tangency, a f of a, and the slope at the point of tangency, denoted by f prime of a, which is how it is read. Any function with a defined slope at a specific point will have one and only one tangent line at that point. So in our diagram, there's our tangent line. And here is our point of tangency. The average rate of change in secant lines is at the top of our next page. A secant line is a line joining 2 points on a function. Finding the slope of the secant line through 2 points, point P is a f of a and point Q is b f of b, will give you the average rate of change over the interval AB. You've known how to do this since your first algebra class, so we just have new notation. This is like your slope formula. You're going to see this a lot. Average rate of change, A rock. Just your slope formula. F of B minus F of A over B minus A. So we're going to use that to find the average rate of change of f of x equals x cubed minus 3x over the interval 1, 3. So looking at your A and B's here, 1 would be A and 3 would be B. So we're going to start by finding f of 1. 1 cubed, 1. 1 minus 3 times 1. 1 minus 3 is negative 2. And f of 3. 3 cubed is 27. Minus 3 times 3, 9. 27 minus 9 is 18. So f of b minus f of a over b minus a. 18 minus negative 2 over 2, 20 over 2 is 10. So your average rate of change at the point 1, 3, or on the interval, 1, 3, is 10. Now we've talked about the average rate of change. Now we're going to look at the instantaneous rate of change in tangent lines. Finding the slope of the tangent line at a point will give us the instantaneous rate of change at that point. However, we only have a single point, so using the average rate of change formula will produce an indeterminate form. Remember that average rate of change formula is going to be over an interval, whereas the slope of the tangent line, our instantaneous rate of change, will be at a specific point. So we need to have another plan. Moving on to plan B, let's choose a second point that is extremely close to our point of tangency. We can call it point Q. Then we can algebraically estimate the slope of our tangent line. All we need to do is add a really small amount, let's call the amount h, to our point P in order to create that arbitrary point Q, and this would give us a secant line. So the first thing we're going to do is we're going to draw our secant line here at A and H to illustrate what we're going to be finding here with our slope. Use the 2 points P and Q in the average rate of change formula. So we're going to do average rate of change to find the slope of the secant line if we were to move point Q directly on top of point P when H goes to 0. So our average rate of change will be F of A plus H minus F of A over A plus H minus A. So we're using our P and our Q, A plus H minus A over A plus H minus A. And this is F of A plus H and F of A. So then we're just going to simplify that to get F of A plus H minus F of A over H, because your A's will cancel here. So whether you realize it or not, what you've just done is you've created a formula to help you find the slope of a curve at a point. Although the slope of the curve is always changing, we know the slope of any line is constant, even our tangent line. So the slope of a curve at a point, the slope of the curve y equals f of x at the point P, A, f of A, is the slope, that's your lowercase m, is f of A plus h minus f of A over h, the limit as h approaches 0, provided that the limit exists. This is called the difference quotient. So that is something that you will need to know. If your instructions say use the difference quotient to, you will need to know what formula they're talking about. Using the difference quotient correctly has some challenges and pitfalls. Let's make sure you understand the notation. So all you're doing in parts A through D, for example 3, is finding A, f of A, and f of A plus h. So we're just going to take our function, we're going to plug in A, what do we get? Then we're going to take our function and plug in f of A plus h and see what we get. So for A, f of A, where you see an x, replace it with an A. For your function, where you see x, replace it with A plus h. So what we're doing here in example 3 is we're prepping for our difference quotient. Part B. Part C. And part C is going to need a little bit of simplifying here. Distribute the 2 FOIL it out, and distribute your negative. And part D. Example 4, given the function f of x equals x squared, use the difference quotient. And notice it doesn't give you the difference quotient. You have to know what that is to find the slope of the curve at the point 3, 9. So we need this piece of information and this piece of information. So let's start with our difference quotient here. Slope equals the limit as h approaches 0. And again, you're using your difference quotient here, f of a plus h minus f of a over h. And as example 3 helped us prep, now we're going to do that prep here for x squared. So if you want to write it right above, f of a would be a squared, and f of a plus h would be a plus h squared. When you FOIL it out, is a squared plus 2ah plus h squared. So now we're going to plug all that in. So slope is the limit. Don't forget that limit notation. Plugging in a plus h is a squared plus 2ah plus h squared minus f of a, which is a squared, over h. Remember, you're doing your limit. So overall, you want to make sure that that h cancels out. So f of a plus h, we're just going to do some color coding here so you know where things are coming from. Now we're going to simplify. As you can see, the a squareds will cancel. And as you also can see, you have a GCF of h in the top, which is what you're looking for. So we're going to take that h out and get 2a plus h over h, and your h's cancel, which is great because at that point, you want to be able to substitute h approaches 0 in to simplify your limit. So the limit equals, or excuse me, the slope equals the limit as h approaches 0 of 2a plus h. And as we have stated, h is equal to 0. So your slope is just 2a. Now we have to finish the problem at 3, 9. So at a equals 3, the slope would equal 6. This would be the slope formula for any value in this problem. So if it said at the point negative 12, 4, actually it would be negative 12, 144, then you would still use this slope formula, plug in your x value to get your numerical slope. All right, now we're going to talk about a really big idea in calculus, which is writing equations of tangent lines. You're going to be writing equations of tangent lines throughout the year. So it's very, very important that you understand what's going on now. Remember that writing the equation of a line requires a point and a slope. Very important. It follows that we should be able to write an equation for the tangent line through a given point, since we can find the slope by the limit process, and we are given either a point or an x coordinate. If you're given an x coordinate and a function, plug x into the function to get the y coordinate. So in calculus, we will focus on using the point slope form of a line. Y equals m times x minus x sub 1 plus y sub 1. You are used to seeing y minus y sub 1 equals m times x minus x sub 1. And all that's happened here is we've solved for y by adding y sub 1. So in example 5, write the equation of the tangent line for y equals x squared at the point 39. Notice this is example 4. So we've already found the slope. Now we just need to write the line. So we know that this is going to be x1 and this is going to be y1. And from example 4, we know our slope is equal to 6. So we just plug our information into our modified point slope formula, which is here. Y equals 6 times x minus 3 plus 9. Keep in mind when you take your AP exam, they're not looking for you whether or not you simplified the equation. So if you left it in point slope form, it would be perfectly fine. Since the slope of a tangent line is a limit, this would be a good place to discuss what happens when limits fail to exist. The slope of the tangent line might not exist because the limit doesn't exist, because you have a discontinuity, a vertical asymptote, or an oscillating function, or because the tangent line has a vertical slope. In the case of a tangent line that exists but has an undefined slope, that is a vertical tangent line, we will use the following definition. A vertical tangent line, if f is continuous at a and the difference quotient approaches positive or negative infinity, then the line x equals a is a vertical tangent line to the graph of f. Now, a vertical tangent line looks exactly like it says, except instead of going, say, by a function, it almost goes through a function, and you'll see an example of that. A concept that's kind of new for us is the concept of a normal line. The normal line to a curve at a point is the line perpendicular to the tangent line at that point. To find the slope of the normal line, use the opposite reciprocal of the slope of the tangent line. So this is going to be perpendicular lines here, tangent line and normal line. And just know that the opposite reciprocal, for example, if the slope is 1/2, the slope perpendicular would be -2. So change the sign, flip the fraction. All right, example 6 has several parts to it. Let f of x equal 1 over x plus 3. Use the limit definition to compute the slope of the tangent line at x equals a. So that lets us know that a should be in our answer. So slope equals the limit as h approaches 0, f of a plus h minus f of a over h. Until you get used to that, it's a good idea to go ahead and write your formula. Keep that limit notation. F of a plus h is 1 over a plus h plus 3 minus f of a, 1 over a plus 3 over h. We have a complex fraction here, so we need a common denominator. Remember, for your common denominator, you'll do cross, cross, across. So cross, cross, across. Don't forget to distribute that negative. Don't forget your limit notation out front. So a plus 3 minus parentheses a plus h plus 3 over a plus h plus 3 times a plus 3 times 1 over h. To get rid of your complex fraction, multiply by the reciprocal of the denominator. So the limit as h approaches 0, I'm going to go ahead right here and distribute that negative, negative a, negative h, -3, so that I can take my next step and combine my like terms. My a's are going to cancel, my 3's are going to cancel, and it looks like I am left with negative h. See that? We've already evaluated that negative by distributing. So I have negative h left over h times a plus h plus 3 times a plus 3. And what we have found and what we have here, which is great, is that our h's will cancel and leave a -1 on top. put that slope back in there just to recall and make sure we know what we're finding. So I have -1 over a plus h plus 3 times a plus 3. And at this point, we are ready to say that h is going to equal 0. So my answer, my slope, is -1 over a plus 3 squared. Now that formula is going to help us in the rest of the problem, which also leads me to the point, if you mess up on part A, part B, C, D, and E are probably going to be wrong. So make sure that you pay real close attention to what you're doing. Part B asks us to find the slope of the curve at x equals -1. So where we see an A, we plug in a -1. Okay, that's -1 over 2 squared, which is -1 over 4. You're probably able to see that we're getting ready to build the equation of the tangent line at x equals -1. We know from part B that our slope is -1/4. We know for our point that x is -1, and we need to find y. So to find the y coordinate of the point, plug x equals -1 into f of x. Very important, something that you will need no matter which tangent line you are finding. So my function is 1 over x plus 3. I plug in -1, and I get 1/2. So now I have all parts that I need to create my equation. Y equals -1/4 times x plus 1 plus 1/2. Remember, if you have questions, to write something in a different color or use sticky notes. In part D, we're going to write the equation of the normal line to the curve at x equals -1. So our slope is -1/4, which means our slope perpendicular will be +4. So all that changes is your value out front. Y equals 4 times x plus 1 plus 1/2. And in part E, use the equation from part C, y equals -1/4 times x plus 1 plus 1/2, to estimate the value of x at -1.1. So where you see an x, replace it with -1.1. So f of -1.1 equals, I'm going to convert everything to decimals, -0.25 times -1.1 plus 1 plus 0.5. This is -0.25 times -0.1 plus 0.5. And -0.25 times -0.1 plus 0.5 is 0.525. You may run up against a problem like that is not calculator active. You should be able to do decimal math. If not, we can catch you up to where you need to be. All right, example number 7, you own it. Given the graph of the function f of x equals 4x minus x squared shown at the right, determine how fast the graph of y equals f of x is changing at 1. In other words, what is the slope of the tangent line at x equals 1? So the first thing I'm going to do, I'm going to graph that tangent line so I know what I'm working with. And one advantage to doing this is as you look at that, you know your slope is going to be positive. You know your graph is increasing at that point. So use your calculator to evaluate the average rate of change the slope of the secant line between the point 1 f of 1 and 1.001 f of 1.001, and be sure to show the difference quotient. All right, so you're using your slope formula, f of 1.001 minus f of 1 over 1.001 minus 1. Again, here's your formula, your equation you're working with. So I'm going to use my store key. 1.001 store as x, and 4x minus x squared. And that's 3.001999. And f of 1 is 3 over 1.001. You should know this. 1.001 minus 1, 0.001. All right, so now we're going to do our math. 3.001999 minus 3 divided by 0.001, 1.999. So the average rate of change is approximately 1.999, which we would round that to 2, but we're being as exact as we can because we have our calculator. So find the average rate of change between the points 1 f of 1 and 1 plus h f of 1 plus h. Average rate of change, again, is going to use that difference quotient. All right, so our formula, again, our equation 4x minus x squared, we're going to do 4 of 1 plus h minus 1 plus h squared. That's the first part. Minus 4 minus 1 squared, all over h. And of course, is our limit. So we have 4 plus 4h minus 1 minus, let's do plus 2h plus h squared minus 3 over h. We're going to distribute that negative. And let's see, we've got 4 minus 1 minus 3, so that's going to give us 0. We've got 4h minus 2h, which is 2h minus h squared over h. Factor out that h, and it's going to simplify to 2 minus h. So before we do our limit, we're going to say our average rate of change is 2 minus h, but h cannot equal 0 because of our original denominator. So what happens to the secant lines between the points 1 f of 1 and 1 plus h f of 1 plus h as h goes to 0? So slope is the limit as h approaches 0 of that average rate of change. Because h is 0, our value of our slope is 2. So as h approaches 0, our slope approaches 2. And that's really just justifying what we found in part A when we got our average rate of change 1.999. It's exactly what's happening here. Find the general formula for finding the slope of the tangent line at any point by using the points x f of x and x plus h f of x plus h. So our general formula indicates that we're probably going to have a variable in our answer. So the limit as h approaches 0, plugging in, And I'm going to write that down here. F of x equals 4x minus x squared. So you can see where these values are coming from. So 4 times x plus h minus x plus h squared. And then minus our function, 4x minus x squared, all over h. Again, remember, we're just using that formula, x plus h minus x gives us h, f of x plus h minus f of x. So we're just using the actual slope formula from algebra. It just looks different because we're throwing our calculus in there. So the limit, as h approaches 0, we're going to clean this up a little bit. 4x plus 4h. Okay, I'm going to do my FOIL method here. X squared plus 2xh plus h squared, so that I can distribute my negative. And distribute my negative again. It is very important that you try not to skip steps here. I don't want you to make a mistake in your problem, get your answer wrong, because you're trying to do too much at once. 4x's cancel, x squareds cancel, and we have the limit as h approaches 0. Let's go ahead and take that h out. H times 4 minus 2x minus h over h. Very nicely, our h's cancel. The limit as h approaches 0 of 4 minus 2x minus h. Again, remember that h is equal to 0. So the general formula for finding the slope of the tangent line at any point, we'll call it f prime of x, because remember our slope is a derivative. H is 0. Answer, 4 minus 2x. As always, let me know if you have questions. Make sure that you mark what you have with a different color or with a sticky note. And we will talk about those when either we see each other in person or through Zoom. Let me know if you have any questions, and I hope you guys have a wonderful day.